All right, so let's take a look at section 4.8. And we're dealing with what's called L'Hopital's rule. It's a French word. L'Hopital's rule. So this has to do with finding limits. Okay, so we're kind of back to looking for limits. All right. Now, the question is, so let's just look at an example here. So let's just find the limit as x goes to 0 of 1 minus cosine of x over x. All right, so if we tried to evaluate this limit right away, we would get a 0 over 0, okay? So let's talk about that. One place that you use L'Hopital's rule is when you get you have a limit that if you evaluated it, the top goes to 0 and the bottom goes to 0. So 0 over 0. These are all called what are called indeterminate cases. All right. So the first case where L'Hopital's rule applies is when you've got the 0 over 0, right? So this top goes to 0 and the bottom goes to 0, right? And so if I want to evaluate that, right, I mean, I've got to do some things to this. And in the past, we've done things like made an XY table, or maybe looked at the graph, or we did some algebraic simplification. There's not a lot that we can do here that helps us with those kinds of things, mostly because none of those things will help us eliminate this x on the bottom. So this is where L'Hopital's rule comes in. Because it's a 0 equals 0 case, this is what it works. This is how it works. L'Hopital's rule says this. It says that if I have an indeterminate case, 0 over 0, I can, instead of evaluating the original limit, I can take the derivative of the top and the bottom. I'm not taking the derivative of that thing as a whole, because that would require a quotient rule, right? But L'Hopital says just take the derivative of the top and put that on top, and then the derivative of the bottom. So, of course, that's going to look like this. L'Hopital's, the derivative of the top, derivative of 1 is 0, derivative of negative cosine is sine of x. And then the derivative of x on the bottom is 1, okay? And notice, L'Hopital's rule says these will be equal, okay? If I want to find this limit, I can instead, because it's a 0 over 0 indeterminate case, I can instead find the limit of the derivative of the top over the derivative of the bottom. Now look at this limit. I can find that. Plug 0 in, I get 0 out, right? There's the value of that limit. That's the thing. Now you can check the graph. You can go back in, and I would encourage you to graph this thing right here and see that as x goes to 0, that the function itself goes to 0. So we are our rules, or we have found the correct limit. Okay, let's try another one. The limit as x goes to 0 of, or no, let's not do that one. Let's do x goes to 1 of sine of x, or sine of pi x over ln of x. Okay, so it looks like a complicated limit here. And so if I try to just plug in a 1, I get sine of pi on top, and sine of pi is 0, right? And then on the bottom, I get ln of 1, and of course natural log of 1 is 0. So again, this is a 0 over 0 case. I don't know exactly what a 0 over 0, or a very small number over a very small number, is equal to. So we can apply L'Hopital's rule, and it says, okay, find the limit, same thing, x is still going to 1, but now take the derivative of the top. So the derivative of sine of pi x is pi times cosine of pi x, right, using the chain rule. And the derivative of ln of x is 1 over x. So this becomes ln, or the limit. We can just leave it like that, I think. So now let's try to evaluate the limit by plugging in a 1, right? And so you plug in a 1 and you get pi times cosine of pi, and cosine of pi is negative 1. So negative pi is what you get on top, over 1 on the bottom, so just negative pi. And there's the limit. Check it out by looking at the graph of this thing, of this function, and see that as we approach 1, the graph approaches negative pi. Okay, and that's not, that's a real slick way to evaluate these limits, is using L'Hopital's rule when we get a 0 over 0 case. All right, let's try one more. So the limit as x goes to 0 of sine of x minus x over x squared. Right? L'Hopital's really comes in handy when you start mixing trig functions with these polynomial functions. A quick look at this. A quick look at this says that if you plug in a 0, or shows that if you plug in a 0, you get it. Sine of 0 minus 0, that's 0. Boom. And on the bottom, of course, you get a 0. So it's, again, it has to be a 0 over 0. Now, there are a couple other indeterminate cases that we'll look at, like, but if it's 0 over 1, that the derivative is just 0. If it's 1 over 0, then the derivative is, or the limit is 0. If it's 1 over 0, then the limit is likely to be positive or negative infinity. Okay, but this one is a 0 over 0 case, and so applying L'Hopital says just take the derivative of the top, so the derivative of sine is cosine of x, minus derivative of x is 1. Remember, we're not using the quotient rule. We're just taking the derivative of the top by itself over the derivative of the bottom. Okay, so now we try it again. Throw in a 0. Well, cosine of 0 is 1. 1 minus 1 is 0. And 2x is 0. So we're still at 0 over 0. But we can apply and maintain this equality, L'Hopital's rule again. So cosine of x, the derivative of cosine is negative sine of x minus 0 over 2. Now plug in a 0, and you get a 0 over 2, which is just 0. And there's our derivative. So these were all situations where we were dealing with the 0 over 0 case.